I'm live. Am I live? I don't know. Hello, everyone. If you can hear this, please put something in the chat box, and that will tell me that I'm not just speaking into the void, aimlessly screaming at no one. Assuming you are there, there's a bit of a lag. So I'm speaking, and then I think about 30 seconds later, we tried to time it yesterday. I think that's when something actually gets to you. So if you ask a question or I type something and it sounds like it's from the future, it probably is, and it'll probably be there in a little bit. Oh, there's a hello. Okay, no, we're all good. 2 hellos. Well, that's more than we need. That's twice as many as are required. In which case, let's go for it. So first things first. I had a microphone and then it broke, so now I don't have a microphone. So if it's too quiet, let me know, and if it sounds dreadful, I can't help that. But I will for next time, if there is a next time. I'm going to try to keep this to an hour, because that's probably how long I have before all the tea I've been drinking all afternoon gets to me. So we'll see how far we get an hour in, and probably call it there. And if there's more to talk about, or there are lots of questions, don't worry, just keep asking them. We can always roll this over to future sessions or however. I honestly don't mind. On that point, there is no stupid question. There's only my poor explanation, so please don't feel like what you're asking is silly or not worth asking. It probably is a good point, and I've just got too excited and skipped over the useful bit. So, assuming I can work this thing. Oh, look, 4 hellos. That's now it's just getting excessive. This is silly. So, assuming everything is working correctly, you can all see this screen. Hello, which is good. This is my one and only slide. There are some instructions about how to set up this project. I haven't run them yet, so you're going to see literally every command I type in. There's no magic behind the scenes. This is a completely fresh and empty directory. If you don't believe me, there is nothing in it. So that's good. The subject of this is going to be Higgledy from first principles. And what I mean is, if the library didn't exist and we suddenly had this idea, how would we know what to write? How would we come to the idea that I came to, and why would it be a good idea, and you know, what problems would we run into? And hopefully we'll kind of step through to a point that we all vaguely understand at least what it's doing, if not how. So I guess the place to start then, and the other thing is, I will try to check these comments regularly, and if I forget, can anyone with my WhatsApp number or Twitter number just nudge me, and it should give me a pop-up, and I'll come back and read it. Cool. So there's a slide. It's very exciting. If we run these things, so this sets up a new Cabal project. It only has an executable. There's no library to it, which is fine, because I think we're just going to do everything in one file. And so with that sorted, the other command just sets up ghcid. If you've never used ghcid before, it is absolutely incredible. It's just a ghci REPL, basically, but every time you save, it just reloads all the files and tells you what's wrong. So if we crack open this, we'll find all the files. So yes, if I do that, look, it reloads and it says all is still good. You might have noticed the -A flag. If that's not something you're familiar with, it's this really nifty thing. If I start a comment with $greater than, and then type an expression and save the file, ghcid will evaluate it and give me the result. So that might be useful later, but it's a very useful trick if you don't know it. So first things first, I want to pose a scenario that we are building an application. You know, we're building the next decacorn, this is going to be, I don't know, WeTube or something. And at some point, someone decides, probably an angel investor of some description, says, we need users. Users are crucial to the growth of any business. And we as good Haskell developers say, well, that's fine. Users are a type of thing. So I'm going to define a user. And there are only three things that are really important about any human being. And they are their name, their age, and whether or not they like dogs, right? That's what we're calling a user at the moment. So we've set up this type, and it's worth being explicit about this. We've, for free, got GHC to give us a way of comparing two for equivalence, comparing two for ordering, and printing them to the screen. So we write this one line of code, and all of that just happens. And that's very useful, and that's very good, and it saves us a lot of boilerplate, because all of these things are very mechanical. There's nothing, in 99% of cases, there's nothing interesting going on here. It's just repeating the same pattern again and again, and changing what's necessary for each individual type. So that's okay. We've got users, that's great. But then we run into a problem, which is, in the real world, if we tell someone to, I don't know, add a user or something, there are, I guess in all but one state of that user, it is incomplete. So while I'm typing in the form to fill in their name, age, and whether they like dogs, I don't have a full user. And maybe I have functionality to save something as a draft, for example. So the thing I am saving is a user-shaped thing, but some of the fields might be missing, right? So if I wanted to model this, the way I would do it in good Haskell is I would create this user maybe type, and it would shout at me for all sorts of very sensible reasons. And all this is it's the same type, but everything is optional, right? So we've still got the same fields, but now I have this notion of a partial user, you know, a user that doesn't have all the information I expect from a user. And so this is useful beyond the scope of just maybe. And so one of the patterns that kind of emerged is this notion of higher kind of data, which I am probably for the rest of the talk going to call HKD. So sorry if that gets a bit confusing. But the idea is there's nothing actually special about maybe. And in fact, what if we just say a user can be, I don't know, anything anything wrapped in some f, right? And I don't care what the f is. It might be maybe, for sure. It might be identity, and if it's identity, I have all these fields, so it's a complete user. But the point is, I can parameterize out this context, this f, and swap it for different contexts depending on what I want the type to do. Real quick, let's start playing this game. Is that enough? Good. Okay. So we've got this type, we've got user f, and that's great. And so we can start messing around with that a bit. We can say that if we have a partial user, for example, partial user f maybe, a partial user could be just Tom, age could be just 26, and likes dogs could be just true. Constructor does not, you're right, it's called likes dogs f. And that's great, so now we've got that. But similarly, fields could be missing, right? So that's how we would use this type. And of course, user f maybe is us saying the f in all these cases is just maybe. Something that might be a little less obvious, which I think is quite neat, is we could also say, I don't know, user inputted user. And if we swap maybe for IO, we can start saying things like that. So we can start saying I'm going to give you, instead of just a string, an int, and a bool, I'm going to give you programs that result in a string, an int, or a bool. Oops, that's not how you spell that. And so I end up with this record that is the same shape. It's still a user-f, but now all the fields are wrapped in IO. So I've got little programs per field. So this is obviously really neat. The partial user and the user inputted user are the same basic code, and thanks to the miracle of polymorphism, I can swap out what I need those two things to do and how I need them to behave. The problem we run into pretty quickly is we start getting too excited, and we say, let's use user-f everywhere instead of user. User is dead to us. We don't need this anymore. User-f is far more helpful. I can do all these clever tricks. And then eventually you get to the point where you start saying, well, come on then, GHC, let's get some instances. And GHC freaks out a bit. The reason it's freaking out is because now I have this parameterized f. GHC's standard, let's just stick with EQ for now. GHC's standard approach to EQ is to say take each of the fields and check that they're equivalent. So the first thing it tries to do is check whether the two names are equivalent. That's the first one on its list. And it hits a problem, which is I can't prove that f string is always going to be something I can equate. I don't have that constraint available. And that's true, if that f is, I don't know, a function from int to something, I don't have EQ for that. So it's not always true that every user f value has an EQ instance. So I need to start adding those constraints. And the way I do it is I turn on another extension called standalone deriving, and I use this funny syntax which says, I can say, I have an EQ instance for user f if I have an EQ instance for f string. So now I'm saying, just as when I'd write a normal instance, I can put constraints on that instance, I'm now saying derive me the code that you would have derived normally, but you have these constraints available, right? Just add them to the code that you're generating, which is good. But then GHC starts to complain with a bunch of problems that are probably quite scary if you've never seen them before. So the first one is looking at this line. GHC, when it's picking instances, when it's analyzing instances, if we say something like, if we imagine the show instance for list, it does this very, very simple check, which is look at the right-hand side. Is the type bigger, in quotes, than the one on the left? So in this case, I've gone from a list of A to an A. So GHC says, okay, the problem I'm trying to solve is getting smaller, and so logically, eventually, I'm gonna reach the nothing case, right? I'm gonna reach a base case, and I'm gonna have solved it and figured it out. So this instance is perfectly legal. The problem here on our line is that GHC is not clever enough to figure out that solving EQ f string is an easier problem than solving EQ user f. It's not super important that we talk about why. It's just the thing to bear in mind when we say undecidable here, when it tells us to turn on undecidable instances. It's sort of a misnomer, because what it's saying isn't that the thing is undecidable. It's saying, I haven't been able to figure out a way to do this decidably. So if you, the programmer, can promise me that it's all going to work out fine, this is cool. You just turn on this extension and I'll believe you. So it's not as scary as it sounds. In general, it would be impossible for GHC to know every time something's decidable or undecidable. I tend to apply the rule of thumb that if it's still compiling after 30 seconds, it's probably undecidable, and that seems to work. It seems to be a good barometer for how GHC is feeling. So now we've done that, we hit the next problem, the next complaint it has, which is, okay, I've figured out a way to compare the two names, but now I'm trying to compare the ages, and I don't know that I have EQ of f int, which is fine, because again, we now know how to keep that happy. We just add the next constraint, right? And then finally it says, okay, I don't know how to equate f bool, and we say, basically, just write me an instance where all of these three are implied, and everything will be fine. And sure enough, GHC is now happy. It says, okay, well, if I know those things are true, if you can supply those proofs, then I can write you an EQ instance. This is okay, but if my record becomes 20 or 30 fields, this becomes a lot of code, right? This is a lot of boilerplate. So generally, there's a trick people play, which is if I turn on one of these fancy new extensions, quantified constraints, I can write a more general constraint here that says you can have EQ of user FF if I know EQ of X, I know EQ of FX. This is a bit weird if you've never seen the syntax before, but what it's basically saying is I know I have EQ string, and now you're telling me that I need EQ f string. I know I have EQ int, I now need EQ f int. I know I have EQ bool, I now need EQ f bool. This constraint says f is one of those types that as long as you can have an EQ on the inner type, you can have it on the outer type. So like list. If we think of the list instance for EQ, it goes something like instance EQ A implies EQ of list A, right? This is that. That's all I'm saying, is if I have EQ for the inner, I have EQ for the outer. And this just generalizes that to say, you know, it's not just list, it's any F. There are two reasons I don't like this. The first is it's quite weird syntax that people aren't familiar with, so it tends to be, I guess, just more cognitive load, right? It's something that's going to trip someone up. And the other thing is, if you're a bit of a purist, this constraint is far too restrictive. We could imagine a type that only has an EQ instance for you know, an inner type of string, int or bool, and now we couldn't use that as our f because it doesn't work for all x. So it's more complicated. It is less code, but it's more complicated and more restrictive. So this isn't a great solution. The other problem you have, and again, we probably won't go into why today, the other problem you have is you would then assume that, okay, well, I can just replace everything with ORD, and GHC will then explode and say, oh, I can't deduce ORD X. And the fix, which is even more cryptic than the error message, is you can just say, oh, and this is one of those that has an EQ instance. So I don't really want to talk about why this is, because it goes into quite a lot about how instance resolution works. But the point I'm trying to illustrate is we can't really avoid ending up with more code than we want, right? It's quite a lot of mess anyway we divide it up. So one of the other approaches we can take is say, well, this is all fine actually. This is okay, because if I ever want to EQ, ORD, or show, I'll just convert back to my original type. So I'll keep user, but also keep user f. And I'll write two functions that say I can construct a real user, a normal user, from a user f if f is applicative. And we'll see why in a sec. And similarly, I can destruct a user into a user f. So if I have these functions, I have a way of getting to and from my HKD type and back to the normal type, the ADT, that has all these instances and doesn't require all the boilerplate. And so in this case, if we think about construct taking a user f, this is just going to be some straightforward applicative shenanigans. Nothing too scary. Oh goodness. Sorry, I'm not very good at Vim, so you'll have to forgive me. So if we turn on that, and sure enough, we see because every field is wrapped in this F, I'm just lifting user over those fields, and that's how I get out again. Similarly, if I want to destruct a user, then I can say that would give me a user F, where the name F is pure name, the age F is pure age, and the likes dogs F is pure likes dogs. Right? So I have these two functions for going to and from my HKD, which is great. That kind of solves a few of our problems. I don't have to worry about the EQ and the ORD instance, and I can just handle a full user in whatever context I want. It's not perfect, but it's enough that we can avoid some of the mess we saw earlier. So a while ago, I was looking at this purely for the maybe case. I hadn't really thought about all this kind of F parameterization at the time. I think it was Sandy McGuire and Chris Penner who nudged me and said you should generalize this. It'd be more useful. But the question I had in my mind was, in all cases, this HKD type is literally just this type, but all the fields are wrapped in some F, which in my case was maybe, but whatever type you choose, it's a completely mechanical transformation from my user type to my user F type. And so it's not satisfactory that I have to I guess define user F at all, right? There's no reason why I should have to do that, because I guess as Haskell developers we kind of feel that if the compiler can do something, it should, right? The whole point of type classes is code generation. I want these things to be derived for me, because the less code I write, the fewer mistakes I inevitably end up deploying. And so there are a number of ways you can approach this. I think the first and maybe most common one would be a template Haskell solution, which says I can read the user type and generate you the user F type. And that's fine, right? That just brings a user F type into scope. We don't need to write it ourselves. It hopefully behaves in the way we would expect it to. But I think at the time I thought, well, I don't even want that. I want some wrapper I can put around my user type, and that sort of transforms it, like read a T or something like that. That just takes the thing I have and just makes it more capable. And I don't want to know how. I don't want any idea of what's going on behind the scenes. I just want this watertight abstraction that just gives me this HKD behavior without me having to do any work. And so I suppose, at least at the time, to the man with a hammer, everything is a challenge for generics. And so that was kind of what I ended up reaching towards. At this point, I think I've covered everything I want to cover about motivating why HKDs are useful and worthwhile, and also how we might define them. So if you have any questions, just leave them in the comments, and I'll keep checking back, because now I want to move on to kind of how we get to what is now the HKD type. Cool. So yes, no questions yet. Good. So at this point, it's worth talking a bit about what generics as a concept introduces to Haskell, and what makes it an interesting field and worth learning and everything like that. And the interesting thing about generics is that for every ADT in Haskell, we can, and this is a very hand-wavy statement, and I'm not gonna spend too much time proving it, we can represent it as a sum of products. So if we have a type with two constructors, we can represent it as an either of the two constructors. And if we have a constructor with two fields, we can represent it as a tuple of two items. So if either is our sum, tuple is our product. And the generic mechanism, through a series of very cryptic names, gives us a way of getting from our regular type into this kind of standard structure, this standard layout and representation. And the reason that's useful is if we can write functions that work on the representation rather than the type themselves, every type with a generic instance, it can now be, applied to the same function. We can write a function that generically shows a type, and every type with a generic instance will now have a way of printing it. There are packages that will give you generic derivations for semigroup and monoid and functor and all of these things, and they all work by saying, if I can tell you how I would construct that instance for a generic representation, and you can turn your type into its generic representation, we can compose the two together, and now everything's happy. So that's the motivating reason why we would care about it. So if we look at some examples, I'm gonna, oh goodness, let's hide all that before anyone sees it, and spoils the surprise. So we open a new, fresh REPL, and let's start asking some questions. So if no one has seen void before, void is a type with no constructors. It has no inhabitants, no values. Void it's nothing. You can't have a value of type void. So in our sums of products way of talking about things, we would say it's a sum of zero constructors, right? There are no constructors in void. If we then ask GHC through the use of this rep function, I will come back to that in a sec, I promise. It gives us some information. It says D1 metadata void data void base false V1. As always, fantastic names. So what it's telling us here, D1 is the generic way of saying data type level metadata. So what we've actually got here is something that says the data type level metadata for void is that its name is void, it's defined in the data void module, which is in the base package, it isn't a new type, and V1 means it has no constructors. It is a void type. Okay, so it's a lot of names, but I'm hoping through lots of examples we'll kind of get used to reading this. I said rep was a function. I said I'd come back to it. Rep is strictly a type family, which means it's a function that works at the type level. So whereas with a normal function we would give it a value, here we give it a type, and with a normal function we get back a value, here we get back a type. So I think maybe the clearest example of this is if we import GHC typelets and get a prompt that is less ugly, because this is just going to grow. And we say, what is the type of the plus function? We get back this, right? This is the plus function we know and love. And in our brains we can say it's int to int to int, or float to float to float, or whatever else, right? It's a function of two arguments that returns their sum. There is a type level equivalent in GHC typelets, which is also called plus, and that is a function from nat to nat to nat. So natural number to natural number to natural number. So at this point, there's nothing really worth worrying about. It's just a thing to bear in mind. If I type :kind, I'm asking about a function at the type level rather than the value level. And so when we talk about generics, I want a way of getting from a type to its generic representation that is a function. It just happens to be at the type level. So it's a bit weird, but we'll get used to it, I promise. So going back to data void, wherever it is, we have some metadata, we have no constructors. It might be interesting to see that D1 is a type synonym for M1D, which I read as metadata for the data type. So we're going to see a couple more cases of M1 as we work through types, but just read it as metadata rather than something intrinsic to the structure of the type we're dealing with. So that's a type with no constructors, and the representation is pretty small, as we'll see. So if we move on to a type with one constructor and no arguments, we could have a look at unit. Right? Unit is a type. It has one constructor, which is unit, and its generic rep looks like this. So we have some data type level metadata. It's a data type called unit. It's defined in ghc.tuple, which is in the ghc prim package. It isn't a new type. It has one constructor, which is called tuple. It is written in prefix. It doesn't have named fields, and it has no fields, no arguments. What I mean by named fields is if I write a record, like we did with user, name, age, and likes dogs, they are names. So in the generic rep, we can see, we get this Boolean flag that tells us whether or not the thing we're looking at has names, which we won't use today, but actually if we do one later on, there's a function in the Higgledy library called labels, which makes use of this. And then yes, U1 means no constructors, so read it as a unit. It is a unit constructor. There is only one value of this constructor, if you like. Cool. Nothing too scary yet, I hope. So let's try a slightly more complicated one. So let's ask, what does the representation of either int bool look like? Right, so either is a sum of two options. It has two constructors. It's either left int or right bool in this case. And so when we look at the generic rep, we get something reasonably scary, but that's okay. If we work from the top, we see that there is data type level metadata. It is called either. It's defined in data either in the base package. It isn't a new type. It has a constructor called left, which is written in prefix, doesn't have named fields. Inside that is an argument, which happens to be an int. We will come back to this. There is another constructor, so it is a sum. This funny symbol here means sum of two constructors, left and right, which again, prefix, no named fields, and it has a bool inside. So we can see, even if we don't understand all the words that are on the screen, we can see that here we've got int, and here we've got bool, and there's this something in the middle. So we can kind of get this vague idea that it's a sum of an int and a bool, right? It might be difficult to parse, but you can see the idea. So the things I glossed over, S1, surprise, surprise, is another instance of M1. I've always read this as selector. I'm sure there is a better name for this, but this is metadata about the individual arguments of a constructor. So in this case, the bool on the right-hand side doesn't have a name. This isn't a named field. It's not unpacked, it's not strict, and GHC decided it was lazy. Do not worry about any of those things. They're irrelevant today. And then within an S1, you get this rec0, which I read as a recursive type. So this is the generic rep's way of saying this is a type inside your type. So this is the bool in either int bool. If we ask what rec0 is, we find out it's a synonym for k1r, where the k I presume means constant and the r means recursive. I presume at some point they thought there were going to be more of these, but the only one you ever see here is rec0. So it's just a series of unfortunate names, really. And the sooner you can kind of just block them out mentally, the better the time you'll have. So now we've seen a sum type, we've seen a sum of constructors. We could say, what does a product look like? So tuple is a product of int and bool. So if we quickly think what we would expect here, This is a tuple, so it's one constructor which has two arguments. So if we can kind of hold that in our minds, this should give you some way of parsing this result. So we have some data type level metadata. It is a tuple defined in GHC tuple in the prim package. It's not a new type. It has a constructor with this helpful name. Inside that constructor, we have a product of a field with no name that is an int and a field with no name that is a bool. Okay? So we have these layers to every generic rep, and they always come in a very predictable form. And if we write this out, I haven't done it yet. Good. The first thing you ever see in a generic rep will be D1 with some metadata, and then what I will call it the inner stuff, but I'm sure there's a better name for it. The thing you see below it will either be V1 if it's a void type, so there are no constructors. It might be a sum of two constructors. It's important to note that the sum and the product form trees, so it's not like a cons. If I have four constructors, this will be a sum of two sums. Okay, so you have to kind of walk that tree. So either V1 for no constructors, a sum for multiple constructors, or we go down to C1, which is constructor level metadata, and inside that we will either find U1, which means there are no arguments. We will find a product, again a tree of arguments, and at the leaves of each of those, or if we only have one argument, we will find an S1, which is some more metadata, and inside that we will find a K1R of the field type. Okay, so these are all the things we're ever going to see in a generic rep. Every type, the conjecture is every ADT can be built out of these building blocks. We don't need anything else. That is enough to build any generic representation. What we're going to do today isn't going to make any choices depending on metadata. So we can actually say, just to simplify things, C1, S1, and D1 are all just M1. Right? So that gets us down to 6 cases. Right? The theory is if we explain what our function that works on a generic rep does in these 6 cases, it will work for every ADT, which is pretty exciting, I think. Cool. Let me check my notes. Have I done everything I wanted to so far? Yes, good. Okay, so next thing on the list is, now I know what a generic representation looks like, how do I get one for user? Because that is a type, and right now, if I save that and come over here and say, what's the kind of the rep of user, GHC gets stuck, which is really annoying. That is not what I wanted to happen. The reason it doesn't give you an answer and just says the answer to rep user is rep user is because there's not a generic instance for user. So we would have to write one. We would have to write out this, I presume that's just going to explode, isn't it? Yes. We would have to write this class here. So we would have to say, what does a rep look like? How do you get from your type to the rep? And how do you get to your type from the rep? Luckily for us, GHC has another glorious language extension called derived generic. And what derived generic does is say if you import GHC generics, as you should, you can just say derive me generic, and it works, which is great. So we've done 0 work, and again we're back to this lovely situation where GHC is writing code, so we can't get it wrong, which is, I don't know, very important to me. I make a lot of mistakes. So now, if we refresh this REPL, we get a representation. And based on what we've seen, this is hopefully something that sort of starts to make sense, right? This is hopefully not too unexpected. So the data type level metadata is it's a type called user, defined in the main module in this package I've called main. It's not a new type. It has a constructor called user, which is a prefix constructor. It does have named fields. The first field is called name, and it is a string. The second field is called age, and it's an int. And the third field is called likes dogs, and it's a bool. So just like that, GHC has just written all this code for us, and we're gonna see as we carry on just how much code it's written for us, and how lucky we are. The thing I think is useful at this point is we say, okay, that's what user looks like. What if we tell GHC that I also want you to write me a generic instance for user F, and I'm going to reload my REPL, and I'm going to say, okay, what's the representation for user F maybe? And again, hopefully, we can look at this and we can say, well, there's some data type level metadata. It's called user F, main false. It's got fields, name F, age F, likes dogs F. But the interesting thing, the thing that sparked this whole project for me, was that looking at this, forgetting the metadata for a second, the only difference between the generic rep of user and the generic rep of user F is that every field inside this rec0 is wrapped in here maybe, but generally some F, right? That is the only thing that separates these two types. So if I know that there is this mechanical transformation that I need to apply to the generic rep, do I need the user F type at all? Because I can just run this transformation and get the user F without having to write all the boilerplate, and I can be sure that it will write the right code because I've generalized away this kind of boilerplate mechanism. And so the way we would approach doing that is we would write this transformation, and we write transformations in Haskell using functions, and we write functions at the type level using type families. So let's write a type family. If this is your first type family, my first impression at least was this is a lot of syntax for very little effort, and for that, I'm sorry, you'll have to bear with us. If you're used to Idris, this will just annoy you. So, in principle, the function I want to write, actually, let's just hide all of this a sec. The function I want to write is a type family that says, let's say it HKDifies some type. So in our case, it's user, but it could be anything with a generic rep, right? According to some F type. Okay, so more extensions. So if everything works, if we get it right, all this function does is take our type and returns the HKDified generic rep. Cool. It turns out with our steps that I've just deleted because I'm an absolute fool, let's put those back. The first thing we need to do is to say HKDifying X according to F means we first have to call rep on it, and then we're going to have to write a different function because you don't have let bindings and you don't have composition and all these wonderful things in type family. So it does become very verbose. So we need to write a different function at this point, which takes a rep. Don't mind what this is at the moment. And basically does what HKDify would do, but with the generic rep. In fact, at this point, assuming I'm still 30 seconds ahead, I can beat anyone to to saying this. This is really actually just a type synonym. So HKDify XF is really just G HKDify rep XF, where G HKDify is the same function, but it works on the generic rep. Okay, so we've taken our normal type, we've used the rep function to get to a generic rep, and now we're back to these 6 friendly cases that we identified earlier. And all we have to do is explain in those 6 cases what we want to do. Okay, so if we start with the first one and we say, I have some metadata and some inner stuff, then to GHKDify that with respect to some f, I want you to basically ignore all of the metadata and just recurse down inside the metadata, right? So the metadata isn't important, just leave it as it is and carry on traversing this tree down toward the leaves. So we've now handled all the metadata. Pat ourselves on the back, huge effort, well done everyone. The next step on our list is to say, what do we do with a void type? So if it has no constructors, how do we turn it into an HKD? And the answer is, it already is one, right? If I have no constructors, there's no difference between, oh, hello, sorry. Let's put some more things in here. Oh, index. Yes. So if I have no constructors, I have nothing to wrap in my f, so I've already done all the work. I can sit back and say, void is taken care of. So I can tick that one off. So the next is, what do I do if I have a sum of 2 constructors? And the answer is, I go down the left side. Oh, sorry, this should be sum, not product. And I go down the right side. Okay? Turn on more extensions. So again, sums, if it's an either of A or B, I just traverse down to the A and I traverse down to the B. So again, I still haven't done anything in this function. I'm just working my way down the tree looking for something important. So that's sums dealt with. The next is unit. If I have no constructors, then, if I have no arguments, then my type is already an HKD because I've got nothing to wrap in the values, right? I've done all the work. Hooray! So that one's another easy one. Looks a lot like void. After that, I then have products. So again, it's not going to be hugely surprising. If I have a left and a right, I walk the tree down both sides. And then finally, once I've gone through the sum of all the constructors, I've gone through the metadata, I've gone through the product of all the arguments, I get down to the thing I actually care about, which is the type of the argument, which is K1RX. Again, sorry, the names are terrible. And what do I want to do now? Well, actually, this is the only useful part, really. This is the only relevant part of this entire function, which is when I get down to an individual argument, I just want to wrap it in the f, right? So when I get down to the name, the age, or the likes dogs, the rep I want to build is just maybe string, maybe int, maybe bool, or io string, io int, io bool. All this effort here is really just to get us down to this line at the bottom that does the actual work, right? This is the line that says wrap every field in F. So it's again, like I say, type families come with loads of boilerplate, ironically, loads of extra syntax, and I think that makes them much scarier than they actually are, because this is just like writing any other recursive function. We could just as easily have said, I don't know, we could have gone as far as to say, at the value level, this would be something like or v1 or, right, rep. It's just a tree, right? And this is just the same way as we would write a value level thing that traverses down to the leaves. It just comes with a lot of ugly syntax and has the word type in more places than we'd normally like. But the point is now we can go back to our beloved REPL and we can say, oh, yes, shouldn't have commented that out. That ruins this whole point. We can take our beloved user F type and we get this generic rep that we've already seen. That's all fine, hooray. But we can also say, well, give me the rep of user and then HKDify user with respect to maybe. And the thing that I think is proper magic is that what we've now got as a result, ignoring the field names, basically, it's the same thing, right? The value we have got is identical to user F. So nothing in that type family, in the code we wrote, ever mentioned user F. We don't need it at all now. We can get to the representation of user F without ever defining user F. There's only one problem left, which is a big problem. If we take a user and we say Tom 26 true, right? This is a user, it's all good. And we use the from function, which says convert from my type to a generic rep. We get this absolute monstrosity, which isn't ideal. And I think it's fair to say no one in their right mind would ever want to work with this instead of the user F value, right? This is not good. And yet this is internally what GHC thinks we're talking about when we talk about representations. So it's not an ideal format. It's not something people are going to want to work with every day. So the question is, how do we hide it? And the big focus of this entire library was really, I want all the benefits of working with the generic rep, but I don't want anyone to know that that's actually what's going on under the hood. I want to do my absolute utmost with some type trickery to make sure no one can see the dirty internals, because if you had to see something like this, you'd run screaming and you'd never use the library again, or I would anyway. So the first step is, how do you hold a value of HKDify user maybe without anyone seeing that that's what you've actually got? And there's a lovely trick, courtesy of Haskell 98, which says if we take a value, so we make a new type, which could be, for example, HKD user maybe. Inside, we're going to say it's a thing of type HKDify xf. Don't worry about the void. We will come back to that shortly. And now what I've got is I've got a new type, and I can, it's a smart constructed situation. I can hide the constructor so no one can see into it. The gruesome internals are absolutely hidden. No one has to know that HKDify is a type family or a synonym that's hiding a type family. No one has to know what void is, because all they get is this HKD user thing and maybe HKD user F. And then we provide the API that makes them think it's still working in the same way as everything they've ever used. And if we do a good enough job, no one ever needs to come looking in the internals. And we've kind of removed the entire use case for writing your own HKD type. I'm going to ignore kind of recursive HKDs for the moment, because that's maybe something we can talk about in the future. I think that's probably an interesting topic. So for now, we've as far as I'm concerned, we've we've got this type that is just HKD user F, and inside it looks exactly like a user F. The only thing we are missing is how do we construct one, and then how do we mess around with it. So the whole of the library basically just gives you a suite of functions to mess around with it, and kind of exposes the API you would expect without you having to without you having to know what's going on inside. I have 10 minutes left of my hour, so maybe the interesting thing to do here would be to try and write the construct function. Actually, no, let's write the destruct function, because then we can at least get to our type. And then next time, if there is a next time, we can talk about getting out of our type again. And maybe it's a function that's interesting to try to write yourself, because again, it's going to be working through those 6 cases and just doing as you're told. So we have this construct function again, but now we want to generalize this a bit further, and we want to say, well, sorry, I said destruct. I've already lied to you. Let's bring you up. So I've got this destruct function, except now it looks like that. So now it doesn't care about the user bit. The function I want to write says everything is so mechanical and boring in HKDs that I'll work for anything as long as I've got this HKD value of it. If I want to write a function that behaves differently for different types, the standard way to do that in Haskell is to introduce a class. A class is Haskell's way of saying I have behavior that is dependent on the type, which is maybe a weird way of framing it, but if you think about EQ, for example, I just call equals equals, and depending on the type, it does completely different things. So a class is just a method of kind of generating that code that is specific depending on the type, which is neat. But this class might look a bit scarier, which is fine. We can step through it. So when we want to write functions that work on generic reps, what we generally do is we write one class called a thing, like destruct. Then we write another class called g something. Again, don't worry about the kind of rep. We can talk about it another day. It's not super interesting. And so this line says, well, destruct is a function from x to HKD xf. Gdestruct will take you from x to the HKDified xf void, right? Oh, hello. You're a friendly error. We'll come back to that. So if I have my sorry, 1 second. Let's clear this out. Okay, annoying. We will fix that next time as well, because that's actually quite an interesting design restriction in this library. So if you go and look at the code, you will notice that U1 and V1 aren't actually in the type family, and there is a very good reason, and it is avoiding this problem. So maybe we'll talk about that next time. It's a problem of inference. So if anyone kind of is vaguely following how type families work, I can't infer what rep is currently, and that's going to cause me some problems. It's an ambiguous type. If I turn on allow ambiguous types, it says, that's fine, don't worry, but whenever you call me, you have to tell me what rep is. That's also ugly, so we'll get rid of that next time. Maybe if we do some usage examples, I'll show you what goes wrong, and then next time we can fix it, because I think there's not a lot of information around on type family dependencies, and it's not a particularly scary topic. It's just completely ignored in literature, which is, hopefully it's going to be a quick thing to fix. So I have my gdestruct class and I have my destruct class. I very simply say, as long as I have an instance of generic for X and I have gdestruct for its rep, I should get a destruct instance. How do I do that? First, I turn on some more extensions, as per. This is Haskell. Probably another one. No, we'll come to it in a minute. So I found this hole, which is fine. The first thing I want to do is once I'm going to do something. I don't know what yet, but that's cool. I'll get to it in a sec. And once I'm done with that thing, I'm going to wrap it up in this HKD. Right now, I get this super hairy signature, which is okay, because I have gdestruct, which, hold on, let's do it this way. So the first thing I want to do based on this is say go from the type I have into my generic rep, and then I probably want to call gdestruct. Are you going to work? Are you going to be good? You're going to start freaking out because these things are all ambiguous. No. Okay. I am sorry. We will fix this next time. I think in 3 minutes it's probably too late to get into type family dependencies. So we're just going to cheat a little bit, turn on some extensions, and hope for the best. Yes, that's fine. That's the one I wanted. Good. F. And then here, I can write that. I am going to do that, and then we'll talk about what all this means. Good. So, are we all still here? We're not all frightened off. So we've had to do a few things here which are really ugly, and I wasn't expecting to have time to write this function, which meant I was expecting to have time to explain what the problem we're having here is. But for now, let's just say what we've done here is we've said I have a function that needs to go from an x to an HKD x. And to do that, I'm going to assume that I've already written the function that that sorts out the generic side of things. It does the generic HKDifying. So if I have that, then the way I get this all to work is I say go from my type to the generic rep, do the generic destructing, and then just wrap it in the HKD, and all the work has been done. Next time we'll talk about these type applications. They're not super important for understanding what's going on here. I would just focus on the fact that we've gone from, which is a function, from a type to its rep. We've then called gdestruct, and then we've wrapped it back up in HKD. If this has all worked, which, spoiler, it hasn't, one would expect an example like destruct true true to have type HKD bool bool, let's say maybe, right? One would expect that to be true. Unfortunately, it's not. And the important thing here is to kind of follow what GHC has done to decide that you're wrong. So it's looked for an instance of destruct, and it's found one, and that instance says X needs to have a generic instance. Luckily for us, it does. And it also needs this gdestruct thing for its generic rep. And that's the point where it got stuck, because we haven't written any instances. Okay? So until we write these instances, we're just going to see an error. The way I tend to work through generic problems is I try to do a step to shrink that error each time, right? So the first instance I would write is to say, assuming I can destruct the inner stuff, I can destruct the metadata layer, right? So if I know how to destruct the metadata layer, then that disappears from the error. It says, okay, well, if you can do that, I'll look for the inner. And at that point, it says, oh, no, this isn't going to work at all, because now I've encountered a product, and you don't know how to do that. And so now I say, okay, well, if I tell you how to do that, then does the error get smaller again? And it says, yes. I did the metadata. I did the products. I did the metadata on the individual field. And now I'm down to that inner type. And so I say, okay, well, at this point, assuming that f is applicative, I can destruct k1rx with f, right? So, because all I am going to do, and in fact I can show you, I can ask GHC what would this function even look like, and it says, oh, you would take a k1 of the thing, and you would return a k1 of a thing, which is fx, and how would you do that? Well, valid whole fits include pure. So I'd probably just write that, right? So again, we've got into some gruesome stuff, and I think if we do this again, I'll probably rewind this 10 minutes and explain how we get around the type application stuff, and then maybe run through this example a bit more slowly. But the place we've got to is that if I want to write this destruct function, I'm again just handling those cases. I start with the 6 cases I have and just pluck them off, and the error gets smaller. Now you'll notice at this point I haven't written anything for U1 or V1, and that's simply because my example 0 doesn't contain a rep that uses them. If I change this to unit, well, I'd get a terrible error. But if I could write code, then that error would appear, right? It would say, I don't know how to g-destruct a unit constructor. So we're only writing the instances for the code we have. I haven't written the definitions of these. Honestly, they're quite dull. In fact, let's just plow through them. Let's just get them written. So to g-destruct some m1 inner, I would need to produce m1 g-destruct inner. This is going to say a bunch of nonsense. And then here, if I want to destruct left, right, I will want to, oh goodness, I want to g-destruct left, g-destruct right. So again, hopefully we can kind of, mentally block out the @ symbols for now and see that what we're doing doesn't look a million miles away from what we did for this function originally. We said metadata is not important. We go down both sides of a sum, we go down both sides of a product, and at the base we wrap the fields in f. And over here in this ugly code, we ignore the metadata. We're just saying g-destructive m1 inner is m1 g-destructive inner, so we're just recursing into it. We recurse down both sides of this product, and then when we get to the base, how do we turn an x into an f of x? We just call pure. And so in this admittedly hurried and probably quite rough explanation, we've built that destruct function. And what's interesting, I guess, is that there's nothing specific to bool here. If we did that, this function would also work. If we turned this into user tom26 true, that would still work. The code we have written is completely polymorphic. As long as the type that we are using has a generic instance, it will do what we want, hopefully. It will take each field, wrap it in maybe, and give us back that HKD. So I guess in conclusion, because I said max an hour, and I think it's been bang on an hour of actual coding. So I'll stop writing there. In conclusion, I probably, if this bit didn't make a lot of sense to you, that's fine, because I think it deserves more time than I gave it. What I should have done is just stop 10 minutes ago, but I got too excited. It's far too exciting. I think the key takeaway is that the generic rep of any type allows us to kind of break every type down into 6 steps. And if we handle those 6 steps, we can write a function that works for any type with a generic instance. So again, I mentioned earlier, there are loads of examples on Hackage and what have you. We can write show, we can write EQ, ord, semigroup, monoid, functor. We can do all of these derivations with generics, because the way we define those classes are perfectly regular and mechanical in at least most cases. So by writing those derivations in generics, we can say, well, assuming that everything works the standard way, just give me that code for free. As I was changing this line down here, as I was changing user to tuple of bool and bool and 3 tuple of bools and whatever else, the thing to notice is that every time I press save, that REPL on the right has just generated me a completely different chunk of code to fill in that value. It's using these classes to generate entirely different programs. And the reason it can do that is because it can convert to this generic representation. I can work with the generic representation, and the two just compose together nicely. So I guess that's the main takeaway, is kind of HKDs are very useful, and we haven't played with them much. I think, again, if we do this again, I'd probably like to focus on how we make type inference better. If that's a useful intuition, if we ever have to write this sort of thing in a class, it's usually a sign that our type inference isn't good. We could be doing a better job. And I think next time I'd like to explain a bit more about what that means, because I think I certainly found it very difficult to find literature that explained how you improve type inference and what to look for in these stages. I think it also might be cool to build a generic lens. So one of the functions the library exposes is a lens called field. So I can say field name or age or likes dogs. And again, it will generate me the lens. I think internally now, actually, it's kind of cheeky, and it just calls out to the generic lens internals. But we can write one from scratch, because I think it's a useful exercise, and it certainly taught me a lot about lenses that I didn't really understand before. So if nothing else, I think if you got to this line and weren't crying, then that's great. I've achieved everything I wanted to achieve. And then next time we can fix inference, we can write destruct, we can write construct, and we can start trying to break apart these functions. I think the other useful thing is once you've seen about 3 of them being written, you realize that all the functions are the same anyway. If you go and take a look at the library and go in the types module, you can see the instance of EQ and ord and show for HKD, and they're all basically the same code. It's really very dull. So with all that, I think we'll call it a day. Thanks everyone for tuning in. I have no idea how this went. I hope it was fine. I hope you could read it. I hope it was loud enough. Toby mentioned earlier that the audio was a bit naff. I'm sorry about that. I've ordered a mic, so if we do this again, it will hopefully sound a bit better. And yeah, if there are any questions, tweet me or write them in the chat box. I don't really know what happens to it after I close this window. maybe it goes. Maybe it all disappears into the void. We'll find out. And if any of it didn't make any sense, then yeah, just talk to me and we can pair on it or whatever. Cool. Enjoy your quarantines. I hope you're all doing well. I hope you all have enough soap and toilet roll and whatever else you need. And see you soon. Goodbye.